If you are stepping into your exam thinking a quick glance at your stopwatch or a simple ruler drop is all it takes to secure top marks, you are falling into a trap that catches thousands of students every single year. Let's completely shatter the most dangerous myth costing you marks in Cambridge IGCSE Physics 0625 right now. Today we aren't just talking about basic measurements. We are going to decode exactly how examiners expect you to handle space, time, and uncertainty so you can actually lock in those elusive top band grades.
Look at this comparison, because this is the ultimate showdown between student expectation and examiner reality. So many of us just assume our single ruler drop or that one stopwatch click is absolutely flawless. But here is the hard truth of physics. Any single measurement is not entirely accurate. It will always have an error associated with it. When an examiner is grading your paper, they are actively hunting to see if you understand this fundamental limitation. If you treat a single data point like absolute perfection, well, your grade boundaries are already slipping away.
To put that into perspective, just take a look at this aircraft flight deck. The measuring instruments you see here are feeding the crew absolutely critical information about the jet's performance. And just like pilots relying on these highly accurate measuring instruments to keep hundreds of people safe in the sky, you need that exact same precision on your exam. Missing standard units, rounding way too early, or just ignoring anomalies, that isn't just a minor slip-up. It literally undermines the entire validity of your physics calculations. Accuracy is completely non-negotiable, whether you're in the air or sitting in that exam hall.
So how do we actually build this accuracy from the ground up? Well, before measurement can even be made, you've got to choose your standard unit. The size of the quantity is then found using an instrument scaled in that exact unit. And here is the kicker. The entire SI decimal system used globally is built entirely on just three basic quantities: length, mass, and time. That is the whole shebang. Everything else you're going to encounter in 0625 physics is based on these three foundational pillars. If you don't secure your units right here, your calculations are going to fall apart later on.
Now, things get really interesting when we handle these units at extreme scales. Examiners absolutely expect you to elegantly handle very large or incredibly small measurements using this powers of 10 shorthand. You need to be able to smoothly transition from writing 4,000 as 4 times 10 to the power of 3, all the way down to 4 thousandths, which is 4 times 10 to the negative 3. It's a required way of writing numbers in physics, and honestly, making a mathematical error here just because you didn't use the decimal system properly, it's a painfully common mistake that ruins what is otherwise perfectly sound scientific reasoning.
So that brings us to a massive question. What is the one specific examiner clue that can literally transform a zero-mark data analysis into a full-marks masterpiece? Well, in just a moment, I'm going to show you the exact practical improvement that changes a flawed answer completely. But first, you need the framework that makes categorizing these basic quantities totally obvious, because how you measure it depends entirely on what you're measuring. Leaving this explainer now means missing the literal key that unlocks the highest marks in practical data handling.
All right, let's dive right into this top-end framework. Knowing the fundamental difference between physical quantities is absolutely essential for accurate measurement. On one side, we have scalars, which, as you know, simply have a size or magnitude. But vectors? Vectors are entirely different beasts. If you measure a vector as if it were just a scalar, like say, measuring total distance instead of directional displacement, your final measurement error isn't just going to be slightly off, it will be fundamentally incorrect.
The crucial point here is understanding that when taking complex measurements, direction is just as critical as size. Vectors, like force and velocity, have both magnitude and direction. So when you are asked to combine two perpendicular vectors to find their resultant, you cannot simply add the numbers together. No way. You must physically account for any difference in their directions, whether you're calculating it mathematically or determining it graphically. Because accuracy in physics isn't just about how much, it's about where it's going.
Okay, so we understand our base quantities and vectors, but how do we physically ensure our measurements are actually accurate? To combat that measurement myth we talked about at the beginning, and to reduce the size of your error, especially for a really small distance or a short time interval, the only reliable way is to measure multiples of the quantity and then take the average of those several measurements. A single drop of a ball or one single swing of a pendulum is practically useless on its own. You measure 10 swings, you measure 20 sheets of paper, and you average them out. This is exactly the practical improvement examiners are actively looking for.
Right, let's put this to the test. It's time for a quick interactive viewer challenge. We're going to apply our high mark framework right now. Concept, evidence, scientific reasoning, and examiner wording. I'm going to show you a classic student answer, and I want you to spot exactly why it loses marks before we go ahead and reveal the solution.
Check out the flawed student answer on the left. I timed the swing and got 2. It is fast. I mean, yikes. This immediately loses marks for missing units. To what? Seconds? Minutes? Years? It has a super vague explanation, and it relies on a single error-prone measurement. Now look at the top band Cambridge-style answer on the right. Measured 10 swings at 20.4 s. Average time equals 2.04 s, reducing timing error. See the difference? This perfectly substitutes values with correct SI units. It applies our method of measuring multiples, calculating the average, and it explicitly tells the examiner that this reduces timing uncertainty. That is exactly how you secure full marks.
And that brings us to your ultimate high-mark exam checklist. Your final mental check before moving on to the next exam question isn't just about writing numbers down, it's about telling a scientifically accurate story. Did you use the correct terminology, knowing your scalars from your vectors? Did you substitute values with the correct SI units? Have you actually supported your conclusions with data from the tables or graphs? And most importantly, did you actively describe practical improvements, like taking averages, to reduce that uncertainty? If you tick these boxes, you are thinking exactly like an examiner.
But, this leaves us with a rather massive, unresolved problem. You now know how to extract full marks for a measurement question. We've fixed the missing units, the vague reasoning, the measurement errors, but how do you actually integrate these highly specific data analysis skills into a full, exhausting exam paper under intense timing pressure? Because knowing the physics is only half the battle. Executing it across a whole paper without panicking, that is the real challenge. Integrating these skills under pressure is exactly what separates good physicists from the top-tier students. The next clue to securing your absolute top grade is waiting for you in our follow-up explainer focusing on the last 7 days revision map. So, subscribe to our YouTube channel Ace the Exams at @AceTheExams_IGCS to excel in your Cambridge examinations, and click on that next explainer right now. But before you jump over there, just think about this. If every single measurement in the universe has an inherent margin of error, how do we ever truly know the exact size of anything? I'll leave you to ponder that. See you over there.